Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the jet propulsion cycles. Gas turbine engines are widely used to power aircraft because they are light and compact and have a high power-to-weight ratio. Aircraft gas turbines operate on an open cycle called a jet propulsion cycle. The ideal jet propulsion cycle differs from the simple ideal Brayton cycle in that the gases are not expanded to the ambient pressure in the turbine. Instead, they are expanded to a pressure such that the power produced by the turbine is just sufficient to drive the compressor and the auxiliary equipment, such as a small generator and hydraulic pumps. That is, the net work output of a jet propulsion cycle is zero. The gases that exit the turbine at a relatively high pressure are subsequently accelerated in a nozzle to provide the thrust to propel the aircraft. Also, aircraft gas turbines operate at higher pressure ratios, and the fluid passes through a diffuser first, where it is decelerated and its pressure is increased before it enters the compressor. Aircraft are propelled by accelerating a fluid in the opposite direction to motion. This is accomplished by either slightly accelerating a large mass of fluid or greatly accelerating a small mass of fluid, or both. A schematic of a turbojet engine and the PV diagram of the ideal turbojet cycle are shown in Figure 1041. The pressure of air rises slightly as it is decelerated in the diffuser. Air is compressed by the compressor. It is mixed with fuel in the combustion chamber, where the mixture is burned at constant pressure. The high pressure and high temperature combustion gases partially expand in the turbine, producing enough power to drive the compressor and other equipment. Finally, the gases expand in a nozzle to the ambient pressure and leave the engine at a high velocity. In the ideal case, the turbine work is assumed to equal to the compressor work. Also, the process in the diffuser, the compressor, the turbine, and the nozzle are assumed to be isentropic. In the analysis of actual cycles, however, the irreversibilities associated with these devices should be considered. The effect of the irreversibilities is to reduce the thrust that can be obtained from a turbojet engine. A thrust developed in a turbine jet engine is the unbalanced force that is caused by the difference in the momentum of the low velocity air entering the engine and the high velocity exhaust gases leaving the engine, and it is determined from Newton's second law. The pressures at the inlet and the exit of a turbojet engine are identical. Thus, the net thrust developed by the engine is, where V exit is the exit velocity of the exhaust gases and V inlet is the inlet velocity of the air, both relative to the aircraft. Thus, for an aircraft cruising in still air, V inlet is the aircraft velocity. In reality, the mass flow rates of the gases and the engine exit and the inlet are different, the difference being equal to the combustion rate of the fuel. However, the air-fuel mass ratio used in jet propulsion engines is usually very high, making this difference very small. Thus, the mass flow rates in the equation is taken as the mass flow rate of air through the engine. For an aircraft cruising at a constant speed, the thrust is used to overcome air drag, and the net force acting on the body of the aircraft is zero. Commercial airplanes save fuel by flying at higher altitudes during long trips, since air at higher altitudes is thinner and exerts a smaller drag forces on aircraft. The power developed from the thrust of the engine is called the propulsive power, which is the propulsive force times the distance. This force acts on the aircraft per unit time, that is, the thrust times the aircraft velocity. The net work developed by a turbojet engine is zero. Thus, we cannot define the efficiency of a turbojet engine in the same way as stationary gas turbine engines. Instead, we should use the general definition of efficiency, which is the ratio of the desired output to the required input. The desired output in a turbojet engine is the power produced to propel the aircraft, and the required input is the heating value of the fuel. The ratio of these two quantities is called the propulsive efficiency and is given by propulsive efficiency is a measure of how efficiently the thermal energy released during the combustion process is converted to propulsive energy. The remaining part of the energy released shows up as the kinetic energy of the exhaust gases relative to the fixed point on the ground and is an increase in the enthalpy of the gases leaving the engine. These are the basic components of a turbojet engine and the TS diagram for the ideal turbojet cycle. Let's talk about some modifications to the turbojet engines. Energy supplied to an aircraft manifests itself in various forms. Some of the energy input is used to propel the aircraft and to overcome the drag force exerted by the atmospheric air. Some of the energy shows up as excess kinetic energy. Notice that for the highest propulsion efficiency, the velocity of the exhaust gases relative to the ground should be 0. That is, the exhaust gases should leave the nozzle at the velocity of the aircraft. The remaining of the energy shows up as an increase in enthalpy of the gases leaving the engine. These last two forms of energy eventually become part of the internal energy of the atmospheric air. The first airplanes built were all propeller-driven, with propellers powered by engines essentially identical to automobile engines. The major breakthrough in commercial aviation occurred with the introduction of the turbojet engine in 1952. Both propeller-driven engines and jet-propulsion-driven engines have their own strengths and limitations, and several attempts have been made to combine the desirable characteristics of both in one engine. Two such modifications are the prop jet engine and the turbofan engine. The most widely used engine in aircraft propulsion is the turbofan engine, wherein a large fan driven by the turbine forces a considerable amount of air through a duct surrounding the engine. The fan exhaust leaves the duct at a high velocity, enhancing the total thrust of the engine significantly. A turbofan engine is based on the principle that for the same power, a large volume of slower-moving air produces more thrust than a small volume of fast-moving air. Another modification that is popular in military aircraft is the addition of an afterburner section between the turbine and the nozzle. Whenever a need for extra thrust arises, such as for short takeoffs or combat conditions, additional fuel is injected into the oxygen-rich combustion gases leaving the turbine. As a result of this added energy, the exhaust gases leave at a higher velocity, providing a greater thrust. Okay, that's all for this task. Thank you very much, and see you next time.